So transition metals have a number of important properties that you're supposed to be aware of for the IB exam. And so just to list them, the IB would expect you to know that transition metals form multiple oxidation states or can exist at multiple oxidation states, that they often display catalytic behavior, meaning that they can act as catalysts. And that can be true both in their metal form, their elemental metal form, or in their ion forms. They also show different properties of magnetism, and they form complexes or complex ions that usually have very distinct, beautiful colors. Now, we're not going to talk about the complexes in this video because that is the most complicated part of their properties, and explaining how they bond and how they form these colors. That's takes its own video or two to get through. So for now, we're just going to talk about the first three of these properties, which are a little bit more basic. So we've already touched upon why they form multiple oxidation states. They can form multiple oxidation states because there's a gradual increase in their successive ionization energies. I guess that says that down here, sorry. So it doesn't take much more energy to remove additional electrons from transition metals, so they pretty much always form a +2 ion, because almost all of the transition metals have 4s2 as their outer electron configuration. So losing those gives them a +2 oxidation state or charge, and then removing additional 3d electrons can give them other oxidation states of +3 and higher. Now the highest oxidation state is for manganese, which +7. Manganese is 4s2, 3d5. So in order to form that +7, it has to lose ownership of all 7 of those electrons, the 4s and the 3d. You'll notice that this table in the data booklet, table 14, shows common oxidation numbers or oxidation states. Now, oxidation numbers and oxidation states, there's a sort of subtle distinction between those two, and we're not going to get into it right now, but again, these are kind of like almost like charges. That's how you can think of it for now. These are the common ones, but we could fill in these gaps with other oxidation states that are possible. For example, scandium can form a +2 oxidation state. It doesn't very often. That's why it's been left out of this table. But scandium can also form that. So this shows the common oxidation states or common sort of charges of these different transition metals, which again is possible because after removing the 4s2, it doesn't take that much more energy to remove additional d electrons, which makes multiple oxidation states possible. We've already gone over this in the naming when we have dealt with the ionic bonding topic. We use Roman numerals to identify the oxidation state or the oxidation number that is on the transition metal. So for example, in this first compound, since we know oxygen forms a 2- ion, when there's 2 of them, there's 4 minuses being balanced by this 1 Ti, this 1 titanium, and therefore titanium must be 4+ or +4. So when we name it, we would say titanium IV oxide. And the naming rules pretty much follow that the metal gets its normal name, followed by the oxidation state, and the nonmetal at the end becomes "ide." Now, if we have one like this, where it's a polyatomic ion, so these different chromium compounds, or this one with manganese, because it's now a polyatomic ion, with oxygen, it tends to end in 8. So this one, for example, is chromium, but it's a polyatomic ion with oxygen, so it's going to be chromate. Now, it adds up to 2-. I know every oxygen is -2. There's 4 of them, -8. And if they add up to 2-, then the chromium must be +6. So that's the oxidation state of this chromium in order to make all the charges balance out. So we could say chromate 6. Now if you look at the next one, very similar, 2-. I know oxygen is -2. 7 of those is -14. Has to add up to 2- from this overall charge, and therefore I know I need +12 from the chromiums. Now there's 2 of them, so each one must be giving me +6. So this is another example where chromium has +6, and it's another polyatomic ion with oxygen, so I can't just call it chromate 6 again. So I call this one dichromate. This one's called dichromate because there's 2 chromiums, but it'd be dichromate and then 6, okay? Whereas this one up here is chromium 6 oxide. So 3 different species where the chromium has a +6 oxidation state. One of them is a neutral compound, so it's called chromium 6 oxide. 2 of them are polyatomic ions, so they're called chromate 6, but one of them has 2 chromiums, so it's called dichromate. So some little subtle details there. Okay, second property we would talk about is that transition metals tend to act as catalysts. Now they can act as what are called heterogeneous catalysts or homogeneous catalysts. Now, as those names imply, heterogeneous means different and homogeneous means same. So we're referring to the state of matter of the catalyst. So if a catalyst is in a different state of matter than the reactants it is interacting with, that's referred to as a heterogeneous catalyst. If it's in the same state of matter, then it would be called a homogeneous catalyst. So a heterogeneous catalyst for these transition metals is often when they're in their pure metal form. So like an actual piece of solid metal usually acts as a surface upon which other reactants can temporarily bind and collide and react. So that's the way that they act as heterogeneous catalysts. So it does have to do with their surfaces. Metals have regular arrangements of atoms, which leaves spaces in between that can fit other particles. So one of the sort of explanations for why metals act as catalysts or why they work well as catalysts is because of the fact that they have a porous surface that can absorb reactants onto it. That doesn't tend to be the answer that shows up on IB mark schemes or in IB paper 1 questions, however. The way that metals act as catalysts, or transition metals act as catalysts, largely has to do with the fact that they can form many stable oxidation states. So it goes back to that thing that we already talked about with the multiple oxidation states, because it's kind of unique that if you were to have, for example, 2 different forms of copper in something, these 2 forms of copper, while they have a different charge, are both positively charged particles of a similar size. So they can exist within a given structure. And so you can have these 2 different forms of copper in a catalyst, and the copper plus can give away electrons, and then the copper 2 plus can regain those electrons and turn back into the copper plus that it started as. So if it loses electrons, it can turn into the 2 plus, and if it gains an electron, it can turn back into the 1 plus. So it can react with something by giving it an electron, and then in a later part of the reaction, it can reabsorb an electron and turn back into its original form. And that's one of the key definitions of a catalyst, or the key properties, is that it doesn't get used up or consumed or changed by a reaction. So the fact that these transition metals can exchange electrons, give them away, and reabsorb them without changing too drastically allows them to interact with other reactants, to help reactants along in their process of changing into products without actually changing themselves. So a short answer to kind of summarize all that stuff I just said is that the key reason why they can act as catalysts is due to their multiple oxidation states. That would be the really distilled down answer that you'll see on IB mark schemes. The homogeneous form of transition metal catalysts are very common in the body. Transition metal ions are at the center of very large proteins and complexes in the human body, which often act as catalysts. So I'm not going to go into the examples right now, but that's how it can happen for homogeneous catalysts. Now, lastly, we have the properties of magnetism. There's technically 3 categories of magnetism. They are diamagnetism, paramagnetism, and ferromagnetism. Okay, they all have to do with electrons and their alignment and their pairing. So for an element to be diamagnetic, all of its electrons have to be paired. And you can kind of remember that one by the di making you think of two electrons, which can make you think of paired. So if a metal has all of its electrons paired, so this would be like an example is zinc. It's 4s2 and 3d10. So all of the electrons in zinc are paired. So zinc is a diamagnetic element. Now I know it's not a transition element, but it's just a good example. Diamagnetic elements are not really magnetic in the traditional sense. They are actually slightly repelled by magnetic fields. So they're not attracted to magnetic fields, they're actually slightly repelled by magnetic fields. Now, there's many paramagnetic elements in the transition metals. A paramagnetic element has one or more unpaired electrons in its orbital, so it has to have at least one unpaired electron. With more unpaired electrons, you become more and more paramagnetic. And under a magnetic field, all of those unpaired electrons act like little tiny magnets themselves, and they can become aligned with the magnetic field, as shown in the diagram, and then they can show attraction towards a magnet or a magnetic field. But for most elements, when you take away the magnetic field, the electrons go back to being randomly aligned, and so the elements don't actually act as magnets. So most transition metal elements are actually not magnetic in the sort of traditional way that we think about a magnet. They can be paramagnetic, which means their electrons are unpaired and will align with an electron field, magnetic field, but they don't act like permanent magnets. That property is reserved for a special few elements. And as the name suggests, it is related to iron. Iron is sort of the classic metal that is magnetic. But iron, cobalt, and nickel actually all display ferromagnetism to an extent. What it means to be ferromagnetic is that normally you have your electrons and they're not all aligned in a particular way. So a piece of iron is not really magnetic until it is subjected to a magnetic field by some other magnet. And when you subject it to the magnetic field, the electrons align. And then when you take away the magnetic field, the electrons stay aligned. And so then it acts like a magnet. So it's the putting the metal under the magnetic field, and then even when you take that magnet away, the electrons stay permanently aligned with that magnetic field. That's what it means to be ferromagnetic. Now, you can undo that with different ways, like using high temperatures or alternating currents can unalign those electrons again. But this is one of the ways that permanent magnets are formed. You take pieces of iron or other ferromagnetic materials and you subject them to strong magnetic fields, and it aligns their electrons. And when they're aligned, all of their little magnetic fields combine and add together, and they make the whole piece of the metal act like one big magnet. Because normally when they're not all aligned with each other, all of the little magnetic fields from all of the little electrons spinning cancel one another out. But when they all get lined up like this, then their magnetic fields combine and can combine to make it act like one big magnet. So you need to know the difference between diamagnetism and paramagnetism in terms of paired, unpaired electrons, and then ferromagnetism being when electrons remain aligned after a permanent magnet is removed.